So, good morning, everyone. Welcome to this exercise session for RobotDynamics. This is exercise 3, controlling a legged robot. I and my co-host will be your TAs for today. I'm Vasilios. We are also joined by Hendrik and Fabian. And today, let's talk about how we're going to put some of the pieces that we learned from the previous slides, how we're going to combine these elements in order to learn how to make a toy version of a legged robot walk. Okay, so I'm just going to give you a quick recap. It doesn't have to be as detailed as the previous ones are, because you're basically seeing more of the same. I'm just going to go over the exercise format, basically outline what you have to do, and then you will proceed to do that. Okay, so I hope that at least some of you have seen this PDF beforehand and are not seeing it for the first time. If you are, that's okay, but please read carefully. I know you're going to be in a rush, but read it carefully. Okay, so what are we dealing with today? I think Marco had mentioned already in one of his video lectures that this is the kind of problem that's mostly inspired by Spot, or a primitive legged robot with an arm attached. So as you can see, clearly we're confining ourselves to 2D. This is just to simplify the problem, simplify it in terms of making it tangible so that you can understand what you're going to do in terms of formulating this hierarchical whole body controller. Plus, you won't need to deal with the peculiarities of working in 3D. So thank God that this example exists. Okay, so let's scroll down. First of all, you might have noticed that there's a set of directories. This project is just organized into these folders. Primarily, what you'll need to care about is, I hope you all have been accustomed to initializing your workspace with this workspace script here. Let me highlight it. This thing. And all you'll need to work with basically is the simulate.m MATLAB script, the main script, assuming you have initialized your workspace. Let me just quickly launch MATLAB over here. And then I can show you some of what you have to work with. 1 second. Clearly, I should have launched MATLAB beforehand. Okay. All right. So before I jump to MATLAB, I just want to point out from the PDF that basically you only have to touch 2 files and run 1 file. So we've confined all the things you need to do into the as few points as possible for clarity. And okay, I'll get back to that in a second. So modeling assumptions. I think you've seen these expressions before in the lecture, hopefully. Basically, what we're going to do is we're going to model this planar-legged robot in the plane. So as I mentioned before, we're going to make several assumptions. One of those is that we're confined to 2D. The robot is comprised of 10 controllable joints, degrees of freedom. 7 plus 3 additional unactuated degrees of freedom for the base. So those are Q1 to Q7, the joint angles, XB, ZB, and theta B, so the rotation around Y. These parameterize the pose of the base. The full equations of motion, as you can see from equation 2, includes all the classic model-based terms, the unactuated base selection matrix, plus the Jacobians corresponding to the conditionally active contact forces acting on the system overall. Okay. Please read these points carefully because they contain some of the hints of what you actually need to, some of the hints for how you're going to formulate the constraint matrices. And basically what we're gonna do is we're gonna realize this block diagram. Now let me zoom in. Oops, it's a bit too much. Okay. All right, so our controller is basically, we're just gonna use a hierarchical optimization scheme in the backend. And what we can assume is operating as inputs are a set of references. So basically what the task at hand for the motion of the body, the motion of the end effector, and what the feet should do. And in combination with modeling approximations, this is why I'm denoting here with the hats. So M hat, B hat, G hat, etc. So this just implies that, okay, we are modeling these. We're assuming that there might be some imperfections, but I mean, here it's perfect because it's MATLAB, but you can assume that you're given as input the model parameters and the references. You use these to derive some computations in order to transcribe everything into this hierarchical optimization as a set of QPs. And then we use this kind of framework to generate some joint torques. Okay. There's some information about the hierarchical optimization. I'll go over the code in a bit. Okay, here are the exercises. All right, let me share the whiteboard real quick, and I'll give you a quick example. All right, so what are we going to do today? Basically, this is a toy problem that contains all the mathematical tools and elements that you would use to actually make something walk. Now, of course, we're not going to make something walk. We're just going to make something actuate the base and move the end effector. But in reality, in terms of actuation, meaning that how we generate a final motion for what we care about, which is the base, feet, and end effector, this is nearly identical to what we actually do on animal. So how we simplify this is as follows. Just as we do in animal, this whole body controller, as we call it, basically this whole body controller is placed in fancy terminology, but in the end, it's a realization of inverse dynamics using quadratic optimization. Now, for those maybe who haven't seen the lectures, when going back, and if you don't manage to complete the exercise today, the exercises which you need to look at, the video lectures which you need to look at in order to have all the knowledge necessary to complete this exercise are video segment S 6.5, 7.5, 8.3, and 9. I'm going to repeat that once more. 6.5, 7.5, 8.3, and 9. Okay? With strong emphasis on the first two. So 6.5, 7.5. Actually, as a hint, I would have a look at 8.3 as well throughout the course of this exercise if you get stuck. Okay, so what are we going to do today? Basically, what we're going to do is we assume that we're given trajectories, right? The red and the green, as you see here in this illustration of my poor drawing skills, we assume those are trajectories which are given. Now, the trajectories can be represented in many ways, but what we assume is like at every single point in time, like that we execute our controller, we are given a Cartesian or equivalent quantity at that point. We don't get a spline or some weird parameterization. We get exactly the position and possibly velocity or acceleration that we need to be at any given time. Okay, and so those are just inputs for us. And what we want to do essentially is we want to be able to track those. So we're just doing inverse dynamics on given set points. Okay, those set points for us right now in this exercise, we don't really care where they come from, but you can imagine in a real scenario that they actually come from some kind of planning module that actually uses maybe some other model, maybe it's an MPC, maybe it's a different kind of system, maybe it's even a neural network that actually looks at the proprioceptive state potentially could even look at the terrain and make this decision about roughly where to go, but then rely on the underlying whole body controller, or AKA this inverse dynamics thing that we're doing, to actually execute the motion. And executing the motion is nothing more than taking those references and executing torques, applying torques on our actuators in order to start moving the robot, to generate accelerations, basically, right? To realize the accelerations, velocities, and positions which are prescribed by the aforementioned trajectories. Okay, 1 second. Okay, I can jump back to the text. Okay, so first exercise. Let's see, oh no, sorry, wrong screen. I wanted to share MATLAB. Sorry. Come on. All right. Okay, the font here is horrible for some elements. That's because of some screen resolution issues in Ubuntu. But I think the green should be visible, right, Hendrik?
Yeah, we can see everything. Thank you.
Okay, great. All right, so let's look at this directory. I'm just gonna go here. I'm gonna go to this exercise. Okay, I need to source it. It's basically only thing you need to do. Then have this in a workspace thing. You run it. Ready to go. Okay, so here are the most important files. The only things you need to touch are these two files: floating base controller and hybrid motion controller. Floating base controller obviously for exercise 2.1 and hybrid force motion controller for 2.2. There's this very trivial controller, joint space PID controller, which is just the default that just makes the robot freeze. This is, you can run as a sanity to make sure that everything works correctly. And you say, okay, you said run the controller, but how do you actually do that? It's a very good question. You do that with the simulate script. And if you scroll a little bit to the middle, you'll see there's a section of commented out snippets. Here, you can just comment in and comment out one at a time. And that's basically just enabling the different controller. So we have provided in pre-built binary form, obviously, the solutions. We will be releasing the solution shortly, like within the next few minutes, but you can run this a solution that's not, you cannot read it, but you can actually execute it by one of these solution files, like so. Okay, so let's say we actually run one of these. You're gonna see something like okay. It's clearly not sharing, so let's share everything. Okay, so you should be seeing this. Then you can spin this baby around, have a look what it's doing. Basically, we just made this 2D robot twerk, kind of. So what it's doing is just executing a motion, a circular motion of the base. Okay. So what's important for you to look at in terms of files, as we said, besides floating base motion control, hybrid force motion control, is the HOPT, this base motion trajectory, and obviously the simulate script. Okay, MATLAB. All right, so let's have a quick look at what this simulate script is doing. Basically, it's selecting a controller, setting up all the visualization, all the modeling elements, and then running a for loop, stepping in the simulation time. Control is decimated with respect to the simulation time, and you're updating a model of the system, okay? The model which we use to actually integrate the physics is this function called CCFD, which is actually implementing the contact consistent forward dynamics. So everything projected in the null space of the contacts, such that we don't actually have to realize some fancy soft or hard contact dynamics as you saw in the lecture for the legs. So for all intents and purposes in this exercise, the feet will always stick to the ground as far as the simulation is concerned. However, your exercise controllers don't make this assumption. So even though you're controlling for the full setup, the simulation, for reasons of simplicity and because MATLAB is slow as fuck, will do everything in the contact consistent null space projection. Okay, one final file before we get started is this HOPT. This implements a hierarchical optimization scheme. And what I want to emphasize for everybody, so you don't get freaked out, you don't have to implement hierarchical optimization we provided. You don't have to implement simulation we provided. The only thing you need to implement, we even extract everything from the model for you. Now, if you're looking at the screen, the only thing you need to implement is I want you to input the necessary quantities with the right, carefully selected dimensions into these matrices. So the only task that you have at hand today is to fill in these matrices and press play. Does it work? Yes or no? That's all you have to do. That's all you have to focus on. Moreover, if we go to the PDF, so let's go through exercise 2 to begin with. So our objective, as I mentioned, is we have some position and velocity pose and twist references for, or at least in 2D, pose and twist references for the base. And all that we have to do is keep the legs fixed, keep the end effector fixed, and make the base gyrate according to this trajectory. The 4 to-dos are basically the 4 sections that you have to fill in. So a constraint matrix and its respective constraint vector. And we also provide hints. So as you saw in the lecture, you need to be able to use the equation of motion and use this kinematic this kinematic constraint or kinematic property, just deriving in time the twist, and use these kinds of expressions to derive those matrix quantities, right? Exactly as you did in those 6.5, 7.5, and 8.3 video segments. Then in hybrid force motion control, you will do one step more by actually giving something to the end effector to do, and that is to maintain a constant contact force along the normal of the surface of the wall, and then while also executing a vertical motion up and down. Again, most of it has been implemented for you, and you only need to fill in the necessary sections. Then there's a questionnaire about just some questions about understanding, and the respective rooms. So for all questions corresponding to section 2.1, please go to room A. 2.2 is assigned to room B. And in this main room, I will be answering questions for the analyzing the optimization scheme questionnaire.